All right, so we're going to go to section 1-6. Hide that. Absolute value inequalities. Okay, so you can do this in your notes packet if you like, or you can simply write this down in your notes. Okay. So the first one says, given that absolute value of x is greater than 3, show that that -5 and 3.1 satisfy this, but that 3 and 2.9 do not satisfy this. Okay, so if we plug in -5 for x, we get absolute value of -5 is greater than 3. Absolute value of -5 is +5. 5 is greater than 3, and we know that's true. Okay, plugging in 3.1, absolute value of 3.1 is greater than 3. Absolute value of 3.1 is 3.1, greater than 3. Aha, that's true also. Okay, I'll show that these are not true. Not true. So we plug in 3 in for x, absolute value of 3. It's greater than 3. 3 is greater than 3. That's not true because 3 is equal to 3. It's not bigger than 3. The absolute value of 2.9 is greater than 3. The absolute value of 2.9 is 2.9, and 2.9 is certainly not greater than 3. So that one doesn't work either. Okay, we're going to go to number 2, which says, because absolute value of x means the distance from the x is the distance from x to the origin. That's another way to define absolute value of x. Okay. What does the inequality absolute value of x is greater than 3 mean? Okay. Well, it means that the distance from the origin is greater than 3. Okay, the distance from the origin is greater than 3. So if we look at what that means on a number line, we've got the origin, and if you want everything where the distance from the origin is bigger than 3, you go 3 out and you want everything further away. Go this way, go -3, and you have everything further, more than 3 units away from the origin. So it would look like that. Okay. Now, write this as an equivalent compound inequality. So you might have learned that if you have absolute value of x is greater than 3, basically what we're doing is we're rewriting this so it doesn't have an absolute value in it. So we're going to split this into 2 different inequalities. The first one says x, notice without the absolute value, x is greater than 3, because in the previous video we said absolute value of x is greater than 3 is just x, absolute value of x is just equal to x when x is already bigger than 0. Okay, when x is positive, then that absolute value of x is just x. And in that case, you're going to just get x is greater than 3. But if x is negative, we have to switch the sign. And then we have to flip the sign of this side. So, or we could say x, when x is negative, we have to change the sign of this. When you change the sign of this, you have to change the sign of the other side, and you have to flip this. So x is less than -3. So you're going to say x is greater than 3, x is less than -3. So on the number line, what that looks like, x is bigger than 3, 1, 2, 3. Don't include the 3, which means an open circle. If it's not or equal to, you would fill that in. 3 away on this side, an open circle, and you're going to go that way. So you get the same answer either way, 2 ways of saying the same thing. Okay, now let's talk about notation. Set notation for this solution set. Okay, says that the set of all x, this part, you have a brace here. The set of all x, and this thing means such that x is less than -3 or x is greater than +3. That's called set notation for this particular set. Okay. Now there's also, notice what we said here. We said x is less than -3 or x is greater than positive 3. We didn't say and because there's no numbers that satisfy both of these. A number can't be both bigger than 3 and also less than negative 3. It only has to satisfy one of these two statements, these two inequalities, in order for this to be true. Now, another type of notation, interval notation, is another important form, a way to write that same interval. In a lot of ways, this is a little bit more abbreviated, and it's kind of simpler. But we want all the numbers, you have to write them in an interval. And your intervals always go from smaller number to bigger number. Okay? So your interval notation, you want all the numbers less than negative 3. So what's the left end of that interval? Well, it keeps going forever. So it actually is going to be negative infinity. All the way until you get to 3. So this is the set of all numbers between negative infinity and negative 3. Oh, that should say negative. Okay. You don't want the numbers between negative 3 and positive 3. So we're just going to say this interval in union with this interval. All the numbers from 3, that's the left end of the interval, and then we'll keep going to the right until we get to infinity. There's our interval notation for the same interval. Okay. And then number 3, and we'll see more of that. We'll see some more examples. Okay. Number 3, we already did. Plot a number line graph showing all real numbers of x that satisfy the inequality. Okay, we did that. Let's go to number 4. So that's already done. Number 4. Given that absolute value of x is less than 5, what does the inequality mean in words? Well, in words, it means the distance from the origin is less than 5. Okay? If you think of absolute value of x as the distance from the origin, it just says the absolute value of x, the distance from the origin is less than 5. Okay? Now, if we're going to split this up into two inequalities without the absolute value, we can say x is less than 5. Notice we got rid of the absolute value and left everything else alone. Or if the x is negative, the absolute value switches the sign. So we're going to say x is now greater than the opposite of 5. We can do both of these things. So if we plot that here, if x is less than 5, 0, 1, 2, 3, 4, 5. Notice it's still an open circle. We're not including the 5. It doesn't say less than or equal to. And then we'll go 1, 2, 3, 4, 5, negative 5, open circle there. Because x is greater than negative 5. Notice these two are going towards each other. Okay? So it actually has to satisfy both of these. It can't just satisfy this one or this one. This would say everything less than 5, whoosh. This one greater than negative 5. It would be everything on the entire number line. It would be all numbers. But it actually has to satisfy both, which is why we've got an and here. So set notation, it's going to be the set of all x such that x, you want to say all the numbers between negative 5 and positive 5. So negative 5 to positive 5. That's the easiest way to write this. You could also write, instead of doing that, you could say set of all x such that you could say x is greater than negative 5 and x is less than positive 5. So these two things mean exactly the same thing. This is the preferred way to write it. Now in interval notation, we just want all the numbers going from negative 5, that's the left end of the interval, to positive 5, the right end of the interval. These are both parentheses because we're not including the negative 5, we're not including the positive 5. Okay. All right, now let's go to the bottom of the page. I'm going to do this on the other side, and I'm going to do 2 more example problems. Okay, now it says A, B, and C, so there's 3 steps. Okay. A, you're transforming the equation, or the inequality, so that it no longer has an inequality in it. B, you're solving for the variable. And C, you're going to sketch and give the interval. Sketch and give solution. We're going to do both interval notation and set notation. So for the first one, we've got 2x plus 7 absolute value is greater than or equal to 12. Okay. So first thing we do, this one's a little harder to look at. So okay, the distance from the origin, because this thing's been shifted and expanded. So easiest way is to just split it up into the two. We say what's in here is either already greater than or equal to 12. Or we're going to say what's in here ends up being negative, so we have to multiply both sides by a negative, so we say less than or equal to negative 12. We did the first part, we transform. We split it into, transform into two inequalities without the absolute value. And then we're going to solve for x. So 2x greater than or equal to 5. So x is greater than or equal to 5 halves, or 2.5. Over here, we're going to say 2x less than or equal to negative 19. We're going to say x is less than or equal to negative 19 halves. Okay, if we want to make these decimals, x greater than or equal to 2.5 and x less than or equal to negative 9.5. Okay, let's write this out on a number line. So we've got 0, 1, 2, 3. So here's your 2.5. And we're including the 2.5, so we'll make that a closed circle. Negative 9.5. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 9.5. Would be about right here. So negative 9.5. We want everything greater than 2.5, less than negative 9.5. So that's going to be an or statement. So in set notation, we've got the set of all x such that x is less than or equal to, notice or equal to because we're including the negative 9.5, or x is greater than or equal to 2.5. Okay, there's our set notation. Interval notation, now notice there's one thing that's a little bit different here. Okay, so this interval is all the numbers going from negative infinity to negative 9.5. So negative infinity to negative 9.5. But notice we want to include the negative 9.5, so it's not a parenthesis. We make it a bracket, and that's what tells you you're including that number. Now we want the or statement, which is the union symbol. And we want all the numbers from 2.5. Notice again, 2.5. We're including the 2.5, so we put the bracket all the way up to infinity. Okay, and that's our interval notation. Now you might have noticed the infinity and the negative infinity are parentheses. Those are always going to be parentheses because those are not actual numbers. They're not actual constants. It's not like you could say, oh, we're including infinity. Infinity is just more of an idea that says we're going on and on and on for all of eternity. Okay? And then let's do the last one on the bottom. So B. Absolute value of 23 minus 5x is less than 18. So we'll split this up into 2. 23 minus 5x is less than 18. Notice we just got rid of the absolute value, left everything alone. 23 minus 5x. And when we take off the absolute value for this one, we have to flip the sign and change this to a negative. Okay, solving, we get negative 5x is less than 18 minus 23 is negative 5. Divide by negative 5. Remember, dividing both sides of an inequality by a negative number, you have to flip the sign. So that's going to be x is greater than 1. And over here, we've got negative 5x is greater than, we'll subtract 23 from both sides, so negative 41. Divide both sides by negative 5. We've got x dividing by negative, we flip the sign. That's going to be positive 41 fifths, or x is less than, that's going to be 8.2. Okay, so drawing this on our number line, got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 8.2 comes in about here. Notice we're not including 1 and 8.2. We want x greater than 1. We want x less than 8.2. Okay. And our set notation is the set of all x such that And since we want all the numbers in between, I usually just write the x in the middle and say the two numbers that are in between, 1 and 8.2. And then interval notation will be all the numbers between 1 and 8.2. The lower end of the interval is 1, the upper end of the interval is 8.2. We're not including either of them. Remember, because the original problem just had less than, not less than or equal to. Okay, so there's your two answers for this one.